Hello and welcome to yet another video of Cornerstones of Math. Today we are going to calculate some areas using integration. So let's jump right into the problem. The shape P given as x squared minus xy plus y squared equals 7 is a tilted ellipse, as can be seen in this figure. And we want to calculate the intersection area of two regions involving this tilted ellipse. In the first question, the intersection area of ellipse P and the ellipse Q given as x plus 2 squared over 9 plus y minus 3 squared over 4 equals 1. So this area right here. In the second question, the intersection area of ellipse P and the circle R given as x minus 2 squared plus y minus 2 squared equals 9. So this area right here. Here, the coordinates of intersection points are already given because finding these points are not the main focus of this video and is frankly boring. So with these given information, let's dive into the first question right away. The truth is, the mathematical principle itself is not complicated at all. It's just applying the basic formula to calculate the area under a curve using integration. As for our case, where A is the area of the region wedged between two graphs, we just integrate the difference between the upper function and the lower function. In this case, integral of the upper part of ellipse P minus the lower part of ellipse Q from x equals negative 2 to x equals 1. In the figures below, the integral of the first term represents this area A1, and the integral of the second term represents this area A2. So essentially, we are calculating A1 minus A2. And as for the second area, let's just use geometry and the simple formula for the area of the ellipse, because calculating the other area A1 is quite lengthy and takes a lot of time. So let's save as much time as we can for A2. You see, there's this neat formula for the area of the ellipse of a standard form x squared over a squared plus y squared over b squared equals 1. Its area is given by pi ab. The derivation is really simple, so I am not going to cover that in detail here. The equation of the ellipse can be easily solved for y, and you apply the trigonometric substitution x equals a sine theta, which you may have learned in basic calculus course. As for our given ellipse Q, we know that it is an ellipse centered at negative 2, 3, having semi-major axis of 3 and semi-minor axis of 2. That is, this blue shaded area is actually 1/4 of the area of ellipse Q. Therefore, area A2 can be calculated by this 3 by 3 square minus the quarter ellipse, hence this, hence 3 times 3 minus 1/4 times pi times 3 times 2, hence 9 minus 3 over 2 pi. So now our concern is to obtain the area A1, which is the integral of the upper part of ellipse P. In order to do so, we must obtain the equation of ellipse P in y equals fx form. So from our equation over here, we can rearrange this in a quadratic equation of y and use quadratic formula to solve for y, which gives 1/2 times x plus square root of 28 minus 3x squared. Here, I took plus sign here because we are looking for the upper half of the ellipse. If we took minus sign instead, it gives the equation for the lower half of the ellipse. So using the obtained expression, A1 can be expressed by 1/2 times the integral of x plus square root of 28 minus 3x squared. Here, this x term can be easily integrated to give the value negative 3 over 4. So we obtain 3 over 2 pi minus 39 over 4 plus 1/2 the integral of the square root part. So now our main concern is to carry out this bit of integral, so let us consider just the integral part for now. There's more than one way to calculate this integral, But let's just use perhaps the most well-known method, which is trigonometric substitution. That is, we let x be square root of 28 over 3 times sine theta. This gives dx equals square root of 28 over 3 cosine theta d theta. Next, we need corresponding theta values for two endpoints of the interval of integration, -2 and 1. In this slide, let's say that theta 1 is the value of theta satisfying -2 equals square root of 28 over 3 sine theta 1, and theta 2 is the value of theta satisfying 1 equals square root of 28 over 3 sine theta 2. Of course, you can express these in terms of sine theta 1 and sine theta 2, which equals negative square root of 21 over 7 and square root of 21 over 14 respectively. Or you can express theta 1 and theta 2 using the inverse sine functions. Spoiler alert, we are going to use all of these. Therefore, the integral in question is now expressed as integral now from theta 1 to theta 2 of square root of 28 minus 28 sine square theta, and dx becomes square root of 28 over 3 cosine theta d theta. Here, it is easy to notice that we have 1 minus sine square theta inside the radical, so this part becomes square root of 28 cosine theta. So in the end, we have the constant term 28 square root of 3 divided by 3, then integral of cosine square theta. So we have this mid result for the integral of the square root part. And let us actually consider the integral of cosine square theta separately, because we are also going to use the result of this integral in the next problem. Of course, the well-known method to integrate cosine square theta is to apply the half-angle formula to change the integrand function into 1/2 plus 1/2 cosine 2 theta. Then we can obtain the antiderivative theta over 2 plus 1/4 sine 2 theta. So we obtain theta 2 minus theta 1 divided by 2 plus 1/4 times sine 2 theta 2 minus sine 2 theta 1. In order to actually calculate the sine part, we need to apply the sine double angle formula and convert this into 1/2 times theta 2 minus theta 1 plus sine theta 2 cosine theta 2 minus sine theta 1 cosine theta 1. Again, this result will also be used in the next problem. For now, let's substitute this into here, which gives, now the constant multiplier becomes 14 square root of 3 divided by 3, and then we have theta 2 minus theta 1 plus sine theta 2 cosine theta 2 minus sine theta 1 cosine theta 1. Now it's time to express this in terms of numbers, using these values of sine theta 1 and sine theta 2. From these sine values, we can also find their respective cosine values as well. Therefore, this integral is equal to theta 2 minus theta 1 can be expressed using inverse sine functions, and then this part can be now evaluated. If we carry out the calculation, this part gives 13 square root of 3 over 28, and if we multiply with this, then it becomes 13 over 2. So now that we have found the value of this integral, now it's time to go back all the way up to right here. Now we know the value of this integral. So let us substitute this integral with this number that we just obtained. Then, multiplied by this 1/2 here, now we have the number 7 square root of 3 over 3 here, then the inverse sine part, and this number now becomes 13 over 4. So adding this and this, we have 3 over 2 pi minus 13 over 2 plus 7 square root of 3 over 3 multiplied by inverse sine of square root of 21 over 14 minus inverse sine of negative square root of 21 over 7. This is the exact value of the area of green shaded region in the figure, And if you want the numerical value, you can just plug this expression into a calculator to find it. So we have obtained the exact value of the area, which is a great achievement, but there is one more interesting thing that I want to explain. You see, after I obtained this result, I plugged this expression into Wolfram Alpha's input tab, and the main reason for that was to check its approximate numerical value. But I found something interesting in the alternate form section. What is this? I mean, what is this? This looks something entirely different from my input expression, especially considering the fact that this expression does not contain any inverse trigonometric values. So how do these two seemingly different expressions have the same value? You see, the inverse sine part of our answer is simply θ2 minus θ1, and we have already found their respective values of sines and cosines. And we can obtain an interesting result if we calculate the value of cosine of θ2 minus θ1. This can be obtained using the angle subtraction formula for cosine. So we plug in values, and if you calculate this, the first term is 5 over 7, and the second term is minus 3 over 14. And guess what we get if we do the subtraction? If we use the common denominator 14, we obtain 7 over 14, which is... And we know that this is a very special trigonometric value, right? This means that in this specific problem, θ2 minus θ1 is equal to pi over 3. Therefore, in our expression for the area A, we can use pi over 3 here, which gives 3 over 2 plus 7 square root of 3 over 9 pi minus 13 over 2, which is the alternate form that I obtained from Wolfram Alpha. And I gotta say, what a beautiful answer! In the second area calculation, the intersection area between ellipse P and circle R. Here we have additional problem, and let me explain that by starting from this intersection point -1, 2 and moving clockwise along the boundary of this shaded region. So first, we move along the ellipse to rightward direction all the way to this rightmost point. Then we change direction and move leftward to reach this intersection point 2, -1. That is, we must find the x-coordinate of this rightmost point of the ellipse to determine our interval of integration. And we need implicit differentiation for that task. So let's do this. The rightmost point is the point where the derivative dx over dy becomes 0 because the tangent line becomes vertical at that point. So from our equation of the ellipse, let us differentiate both sides with respect to y. Obviously, because x is dependent on y, we have to apply the chain rule when differentiating x terms, which leads to this result. Differentiating x squared gives 2x times dx over dy, and as for the next part, we have to apply the product rule, which gives this part. And differentiating y squared gives 2y, and on the right hand side it is the differentiation of constant, so it gives 0. From here, it is easy to obtain dx over dy is equal to x minus 2y divided by 2x minus y. When dx over dy equals 0, we have x equals 2y. And we substitute this into the equation of ellipse P. Then we have this, and from this you can easily obtain the value of y, and from x equals 2y the value of x. Here the positive root is chosen because at this point y is obviously positive. The negative root is for this point. Therefore, this rightmost point is 2 square root of 21 over 3, square root of 21 over 3. Therefore, our calculation of intersection area A is now split into two different intervals. First, from x equals -1 to x equals 2, we integrate the upper part of ellipse P minus the lower part of circle R, which gives this area right here. Next, from x equals 2 to x equals 2 square root of 21 over 3, we integrate upper part of ellipse P minus the lower part of ellipse P, which gives this area right here. And quite naturally, let's first consider only this region. For this first integral term, we can also use some geometric knowledge. You see, our circle is centered at 2, 2, having radius of 3. Therefore, this blue shaded region is a quarter circle, hence its area is 1/4 times the area of circle R. So as for this part, we split into this area at the top and this area of the quarter circle and add them up. The red area is the integral of the upper part of ellipse P minus 2, because this line right here is y equals 2. And then we have the blue area, 1/4 times area of circle R. Therefore, we have the integral of the upper part of P minus 2 times 3 plus 1/4 times pi times radius 3 squared. So in the end, we have the integral of the upper part of P minus 6 plus 9 over 4 pi. So we have this, and then we move on to the equation of ellipse P, which gives this. We have already obtained the equation for the upper part of the ellipse in the previous problem. And as for the lower part of the ellipse, all we need to do is to switch this plus sign into minus sign. So we have 9 over 4 pi minus 6 plus 1/2 times the integral of x plus square root of 28 minus 3x squared from -1 to 2. And if we simplify this part, we simply have square root of 28 minus 3x squared, so integral of this from 2 to 2 square root of 21 over 3. And at this point, you know the drill by now. First, we integrate this easily integrable x part, which gives 3 over 4, and this leads to the constant part, 9 over 4 pi minus 21 over 4. And as for these radical parts, we use the trigonometric substitution again, which is exactly the same trigonometric substitution as we used previously. But now we need 3 different values for theta, corresponding to x values of -1, 2, and 2 square root of 21 over 3, respectively. Let's call them theta 1, theta 2, and theta 3. Then we have these sine values. As you can see, sine theta 3 equals 1, because this and this are equal. This means theta 3 equals pi over 2. And let's also compute their cosine values as well, since we are going to need them later. So by applying trigonometric substitution, we have this. And just like the previous problem, this simplifies to the integral of cosine square theta. And as for the integrals of cosine square theta, let's use this previously obtained result, now using new trigonometric values for theta 1, theta 2, and theta 3. Now this is nothing more than a dull calculation, so I will speed up a little bit. As for the integral from theta 1 to theta 2, we obtain the value 1/2 times inverse sine of square root of 21 over 7 minus inverse sine of negative square root of 21 over 14, and then plus 13 square root of 3 over 56. And as for the integral from theta 2 to theta 3, now making good use of the result that theta 3 is actually pi over 2, we obtain the value 1/2 times pi over 2 minus inverse sine of square root of 21 over 7, then minus square root of 3 over 7. And naturally, we substitute integrals of cosine square theta with the previously obtained values, and this step finally removes all integrals from the expression for a. From this point, it's just simplification. if you distribute this and expand, you will obtain this part. And if you distribute this and expand, you will obtain this part. So we have this pi term and this pi term, and this number and this number and this number. And notice that we have the inverse sign of the same value here and here. This means that these two terms can be combined. In the end, we have the result 9 over 4 plus 7 square root of 3 over 3 pi minus 6 minus 7 square root of 3 over 3 times inverse sine of square root of 21 over 7 plus inverse sine of negative square root of 21 over 14. At this point, some of you might wonder whether there is an alternate form that does not contain any inverse sine terms, just like the previous problem. But sadly, that is not the case this time. Actually, for this problem, you can show that theta 2 minus theta 1 is also equal to pi over 3, but this fact doesn't fully eliminate the inverse sine terms, so I don't think it's worth mentioning in detail. Anyway, that was all for today's video. If you watched all the way to this point, then thank you very much for watching. Please go check my other videos as well, such as this hyperbolic substitution video at the top. And also please don't forget to hit the like and subscribe buttons, and I will see you in another video.